to go longer, but after an hour, if somebody gets up and leaves, it's not considered rude.
Yes, yes, I see. No, I will. The talk will not last more than an hour. That's.
You'll be disappointed when you're finished. Go longer.
Then I can give another talk probably at some other point.
Somebody can introduce it. I can do it. Okay. So, well, it's my pleasure to introduce Kavvadias from MIT, and he's going to speak to us about some recent progress on the Schramm-Loewner evolution and Liouville's quantum gravity.
So first of all, I would like to thank the department for giving me the opportunity to give the colloquium and also meet so many great colleagues in the department. So let me start by giving you an overview of the talk and also of the conduct of the main mathematical objects and also the structure of the talk. So the main mathematical object for today is that of Liouville quantum gravity with parameter gamma, or just LQG. Gamma LQG. This is a one-parameter family of random surfaces, parameterized by some number between 0 and 2. So here you can see some very nice simulations of how, not made by me, but by Jeremy Bettinelli, of how such a surface can look like. So here you can already see the fractal nature of the surface. And these two are different, of course, surfaces. Liouville quantum gravity was introduced in the context of string theory in order to describe certain models, and it has connections, it has deep connections with many other objects coming from statistical physics, just like random planar maps, lattice models such as percolation, Ising model, loop-erased random walk, self-avoiding random walk, etc., and also Schramm-Loewner evolution, or just SLE. This is another main object of today's talk that I'm going to discuss about towards the end of the talk. It is not trivial to make sense of, but however, it has been made sense of in a rigorous way. It has been a very active research area in probability during the last 15 years. Gamma LQG, when the parameter gamma is equal to 0, this corresponds to the Euclidean space, so therefore we get a smooth surface, but when gamma is positive, then we get a fractal surface, as you can see also here from the simulations. In this talk, I will discuss four main contributions that I have made to the theory. First, together, of course, based on single author work and also work with other colleagues. First, I will discuss about heat kernel estimates. We will see that there is a concept of a heat kernel on such surface, and I will describe some sharp estimates on the corresponding Liouville heat kernel. Then I will discuss about some properties of geodesics, shedding some light on the geometry of the space. And we will see here there are some different behavior compared to the Riemannian setting. I will comment on that, of course. Then I will discuss about results in continuity in gamma, in the sense we will see that those spaces, these gamma LQG spaces, they have some kind of stability behavior. If you perturb gamma continuously, then those spaces change in a continuous way. We will see precisely what this means. And finally, I will talk about some analysis questions, which I find extremely interesting. I will talk about how the concept of conformal welding and conformal mobility fit well into the theory of LQG and also its relationship to SLE. Okay. Now let me give you first some intuition of how to pick a surface at random in the continuum. So here, first of all, recall the uniformization theorem, which states that every Riemannian surface, which is homeomorphic to a unit disk, can be conformally mapped to the disk. Then, if you study the metric for the surface, it has this nice form here. It's e to the some smooth function times the Euclidean metric. Therefore, this means that we can parameterize these surfaces which are homeomorphic to the unit disk with smooth functions. Therefore, if we want to have, at least at the heuristic level, of course, some kind of probability measure on the set of surfaces, it suffices to have a probability measures on the set of functions of the form rho.
You don't like the complex plane, so you believe only in the disk.
Excuse me?
You don't like the complex plane, so...
Oh, I see. Yes. So when rho is equal to 0, then obviously we get the unit disk. When rho is a harmonic function, then we get a surface which is flat. And the main question here is what type of measure someone can have on rho, at least at the heuristic level, of course. And the point is, we would like our surface to be a random perturbation of a flat metric. Therefore, it is very natural, at least again at the heuristic level, to choose this function to be as the canonical perturbation of a harmonic function. Random, of course, perturbation. And what that object might be, and the answer is the so-called Gaussian free field, or just GFF. The Gaussian free field on some subdomain D, let's say of the complex plane, at a heuristic level intuitively is essentially a Gaussian measure whose density is given with respect to the Lebesgue measure on functions, is given by this exponential here. So here we have this exponential, and here we have the Dirichlet energy of the function. Of course, this object does not make literal sense, of course, but it can be made literal sense, and it's not that hard to do that by just approximating the corresponding quantity by discretizing this quantity by considering the Gaussian free fields on lattices, and then somehow taking the Mace limit of the lattice 10 to 0. Because on a lattice, the Lebesgue measure of functions is well defined. At the end, it turns out that this object can be well defined, but it's not a function. It's only a generalized function, so it lives on the space of distribution. So in other words, it's not literally defined point-wise. And of course, it is a natural perturbation of a harmonic function. And the reason for that is that harmonic functions are the minimizers of the Dirichlet energy with prescribed boundary conditions. And this simulation of how the Gaussian field looks like, so you see here this is a very rough object, you see these fluctuations that go up and down. This is described by Brownian motion. And so you see this is a Gaussian free field in a very large box, and we take the size of the box 10 to infinity. And of course you expect the object that you get in the limit to be to not be a function in the classical sense, but rather a generalized function. And now that I have motivated you a bit about how to pick a surface uniformly random, let me tell you about what Liouville cannon gravity is. So here essentially we just fix a parameter gamma between 0 and 2. Some domain, we fix some subdomain of the complex plane, and we consider an instance of the Gaussian free field on that domain. Then LQG essentially is the random surface whose Riemannian metric tensor has this form, is e to the gamma h times the Euclidean metric. But of course note that in that case h is a distribution, of course. Which means that this does not make literal sense, because distributions are not well defined on points. But however, you can make sense, rigorous sense of that, using some kind of regularization procedure. You can approximate the field here, say, by smooth functions, and for smooth functions, this quantity here is well defined. And you can still define the corresponding quantities. You can still define a constant of an area measure, for instance, like this. You can still define a constant of a distance, like this infimum here, where you take the infimum is taken over all paths, continuously differentiable paths connecting to 2 points. So here this is some parameter on gamma, and this is the regularization of the field. And then by scaling appropriately, we obtain non-trivial limits. So here, this should correspond to the volume measure, for instance, if you are in the context of the Riemannian geometry, and this should correspond to the distance function.
Sorry, what's this C?
Psi here is a function of gamma, some continuous function of gamma. It's essentially what the precise value is, gamma over the Hausdorff dimension of the LQG space. So it doesn't have an explicit form, by the way, because the Hausdorff dimension of those spaces is unknown as an explicit function of gamma. We have very good approximations, but not an explicit function of gamma. And psi of gamma will be gamma over the Hausdorff dimension of that space.
So this is not that metric up there. It's a modification of that metric.
Yes.
C. Does C depend on the parameter epsilon?
No. This psi here depends only on gamma. It's a function of gamma. Yes. On the dependence on epsilon lies on the choice that we choose to approximate the field here. This h epsilon here. So here the resulting object is a fractal object. It's not a smooth object. And this has certain consequences in the meaning that a lot of properties that hold in classical Riemannian geometry do not hold in the context of LQG. And I'm going to talk about the main results that I'm going to describe earlier, such as heat kernel estimates, and also properties of LQG geodesics, as we're going to see. They are very, very different. They're very different from the Riemannian setting. Okay. Now, this was more or less at least definition of LQG. That's what we mean when we say LQG. And now let me follow a slightly different approach, which is quite useful in probability. One very intuitive way to construct a continuum object is to discretize things, to just consider the random discretized version, a random discrete surface, and then take a limit, and then as the number of inputs tends to infinity. And the most natural discrete object that someone can consider in this context is a random planar map. What is a planar map? A planar map is a graph in the plane which is embedded in a way so that no two edges cross. This space can also become a metric space with respect to the metric distance, to the graph distance on the graph. Now, here we need random, of course, planar maps. So what is the most natural measure to define on the set of planar maps? So here, suppose that we have the set of planar maps with n number of edges, say, modulo graph isomorphisms, of course. Then this is a finite set. Therefore, the most natural measure to define on a finite set is the uniform measure, meaning that the probability that a fixed planar map appears is 1 over the total number of such maps. This is the most natural measure to consider on a finite set, of course. However, we can also choose more complicated measures, which are non-uniform measures, where some maps are more likely to appear than others. So we can also consider a variety of measures on the set of planar maps. Then gamma LQG arises as the scaling limit of these metric spaces. So when you take the metric, you scale it up to subfactor, and then you tend the number of input tend to infinity. And then in the limit, you get something continuum. You get the metric that we discussed earlier. You also get the volume form, the area measure that we discussed earlier. The case when gamma is equal to 0, as I mentioned earlier, this corresponds to the Euclidean grid by just taking the mesh size to tend to 0.
So I just want to understand.
Yes.
So how do you get from this map a metric? So let's say, what's a discrete metric?
The graph distance. So
Graph distance.
yes, the graph, exactly. When the embedding is fixed, you just fix to.
When you say metric, you mean like the distance function?
Yes, exactly. That's a very good point. Thanks for the clarification. Yeah, yes.
So the limit is supposed to be gamma LQG, but I didn't notice a gamma in the definition of the graph. So
Yes.
does it come into the non-uniform choice of the maps, or where does the gamma come in?
Excellent, exactly. Usually in the non-uniform measures, we pick some planar maps and we weight the graph by the Laplacian of the discrete Laplacian of the graph. So we take the map, we take the uniform measure, and we weight it by the discrete Laplacian of the corresponding map, up to some power.
You mean like its base eigenvalue or something? Or what do you mean by weight, by Laplacian?
By the determinant of, yes, by the determinant, yes, to some power. And the point is that's where this gamma appears. This power has some explicit form. And when gamma is equal to square root of a/3, this exponent becomes 0. Therefore, you do have the uniform measure. That's the connection with random planar maps. That's an excellent point. And when gamma is equal to square root of a/3, as I mentioned, this corresponds to the limit of uniform random planar maps. And the reason why we get, one of the reasons, of course, there are many ways to explain that one reason why you have this special value is that somehow there is a strong coupling between, meaning that they can live on the same probability space, and square root of a/3 with quantum gravity and SLE 6. So there's a way that these two objects interact. I'm going to discuss about it later in the talk. And the point is that SLE 6 arises as the scaling limit of interfaces in percolation. And percolation here are indeed described by uniform planar maps. So that's where this object here, this specific value comes from. When gamma is not 0 square root of a/3, then we get it's the scaling limit of non-uniform random planar maps. So this is an alternative way to think about these objects.
So you have a disk
Yes.
with a graph inside it. Don't you want the metric on the disk, or is it on the graph?
The graph is embedded in some way, say on the disk,
Yes.
and then you have a graph embedded on the disk. Therefore, you can make sense of its graph distance after you have the embedding.
But it's not the metric from the disk restricted to the graph or anything like that. It's the graph distance.
Yes, the graph distance,
It's like
exactly.
a combinatorial object on the graph itself.
Yes,
You take a limit of that, you end up with the metric on a planar domain.
exactly,
Oh,
exactly.
I see. Okay.
Yes, that's exactly the point.
Okay.
Exactly.
Gamma equal to 0, is it the standard Riemann sphere?
Yes, yes, exactly. It's the plane.
Not the Riemann sphere.
No, it's a flat. It's say a planar domain.
I started with the disk. Okay.
Yes, exactly.
Is gamma non-negative?
No, gamma is only positive. Yes, when it is negative, I don't think you get something which actually makes sense at the end. Okay. And now here I have a very nice simulation made by Jason Miller. So this is a specific bending. This is because, again, of a graph, especially of a uniform quadrangulation. It's a special type of planar map chosen according to the uniform measure, where here this is the so-called circle packing bending, where each disk here corresponds to a vertex on the graph, and two disks intersect if and only if there's an edge connecting them. So in this way here you have a specified bending of a planar map, and different colors here indicate different concentrations of vertices on the planar map. So this is a specific way to actually embed a map. Of course there are plenty of other ways, and in the limit you get LQG by taking graph distances here and also area measures.
Given a diagram like this, you take the centers as the vertices, and when two circles touch, make an edge.
Exactly.
Connects them.
Exactly.
And it's a well-known theorem, but maybe not well-known to everyone in the room, that given a planar graph, there is such a disk drawing of it.
Exactly. And in the limit we get LQG, parameterized by the unit disk. This is a specific example. Okay. And now that I have given you a brief overview of the objects and where exactly they come from, what's the intuition, I have also presented two different ways to think about these Liouville quantum gravity surfaces. Let me start presenting the first main result of today's talk. And the first main result concerns estimates on the heat kernel. In general, as we will see, in Riemannian geometry, of course, it's very important to have sharp estimates on heat kernels. This has a lot of consequences. One of the consequences is because we can understand better the spectral geometry of the surface, in the sense that we can obtain very nice asymptotics of the eigenvalues of the Laplace-Beltrami operator and prove similar loads like the Weil's law. That's one application of that. Another application, of course, is to actually, if we have sharp estimates of the metric, we can on the heat kernel, we can actually recover the metric. There's a way to actually recover the metric, and that's actually one of the, this relates to the so-called heat kernel conjecture towards LQG that I'm going to discuss. That's my main thing, my main contribution towards that is the heat kernel conjecture, essentially, the solution when gamma is square root of 8/3. Okay, but let me now briefly review some general theory on Riemannian geometry. So here suppose that we have a connected Riemannian manifold. Then for such a manifold you can define the Laplace-Beltrami operator, which has some explicit form in local coordinates. We won't be interested in this explicit form, it's just that it does have some explicit form, which is essentially the generalization of the standard Laplacian on Euclidean spaces. One of the main properties of this operator is that it is symmetric with respect to the Riemannian volume measure here. And starting from the Laplace-Beltrami operator, we can actually define its heat semigroup. Now, what is the heat semigroup? The heat semigroup is essentially a family of operators parameterized by time, which live in the L2 space here. They're self-adjoint, they solve a certain version of the heat equation here, and they have this initial condition. And what is then a heat kernel? The heat kernel essentially is a function of three variables which actually encodes this operator, this family of operators, meaning that you fix a time and you evaluate your operator at some function f, then you have this explicit integral form. In the case of Riemannian geometry, it turns out that the heat kernel exists and it is unique. So you do have existence of this function. Okay. Now let me give you one example so that I can actually motivate you a bit. So here the example is in the case of the Euclidean space of dimension 2. So in that space, there's a connection with probability, in the sense you can express the heat semi-group at time t evaluated at the function f as the expectation of the image under f of a certain random process evaluated at time t. So it has some connections with probability theory, and also the heat kernel here has some explicit form. It has this Gaussian behavior, as you can see. And this process here is the so-called two-dimensional standard Brownian motion. So this process is a continuous process that lives in the complex plane, and it has a fractal nature. It is non-differentiable. And you can see here in the simulation, this simulation of the two-dimensional Brownian motion. The green dot and the red dot are the starting and ending points of this Brownian motion. And this process here is not space-filling, but it is almost space-filling in the sense that it hits every single ball in the complex plane with probability 1. And it has this connection here with the heat kernel theory in the Euclidean space in dimension 2. Then the very natural question now that arises is whether we can define heat kernels on an LQG surface. This is highly non-trivial, of course, because it's a fractal object. We are not living in the context of the Riemannian geometry anymore, so it's not obvious a priori whether a concept of a heat. Yes?
Well, these surfaces you said were limits of planar graphs. And on a planar graph, you can define a random walk, you can define a heat kernel, you can define everything. Are the objects on the limit of the graph versions of them, or is there not a close connection?
Yeah, it's related very deeply. Yes, as I'm going to explain now, the diffusion process, which in that sense, which describes the heat kernel behavior, are scaling limits of random walks on a planar map. So there's a very deep connection. That's a very, very good comment. I'm going to comment on that on the next slide. So here the main difficulty then on constructing the heat kernel is that if you consider the Laplace-Bertrand operator associated to LQG, you can make sense of that again via regularization procedure again. It's hard to describe in terms of functional analytic points of view in order to actually be able to understand what the heat kernel looks like. However, here there's a main idea motivated by this example here, that instead you can analyze the diffusion process, which actually encodes the heat semigroup instead. And let me now give you some background of some work towards the area. A series of very nice papers by Berstiki, Garban, Rode, and Vargas actually prove that such a process exists. So there exists some random process, let's call this process Z, which actually encodes the heat semigroup. And of course, this expression satisfies the usual condition, self-adjoint operator. On the L2 space, this should be considered, this measure, as the analog of the volume measure in the Riemannian geometry, now in the context of LQG, and of course with the appropriate boundary conditions, initial conditions. And they also proved, the same authors, that the Liouville heat kernel exists. So there exists a heat kernel here which corresponds to this expression here, to this heat semigroup. And it is well defined and it is continuous with probability 1. So this is something that they actually proved. So it does exist. Now, one quick comment about this process, because it will be important about obtaining heat kernel estimates, is that essentially what this process is a reparameterization of a Brownian motion. And this is related to the comment earlier about random walks, as we shall see. And here in this reparameterization, locally, the time change essentially is given by the volume, by the LQG area measure. Now, the first main difference that we observe compared to Riemannian geometry is that the Liouville heat kernel has sub-Gaussian behavior. This was already observed also due to some simulations and also due to some earlier work that I'm going to mention here. So that's the first main difference that we see today compared to the Riemannian geometry. And this process, this diffusion process, which encodes the heat kernel in this context, is the so-called Liouville Brownian motion. That's how it is called. Again, you can just imagine it as a regular Brownian motion in 2 dimensions, where it is parameterized in a way which depends on the surface, depends via this volume measure. Okay. And now, to make the link with the discrete picture, is remember, the 2-dimensional standard Brownian motion in the complex plane arise as the scaling limit of the simple random walk in the Euclidean grid. Where here a simple random walk is essentially a random path where at each step goes with equal probability one position up, down, left, or right. And the limit is the Brownian motion, the standard Brownian motion. Now in the context of LQG, you have the same thing, but the random walks now do not live on the standard Euclidean lattice. They live on a random planar map instead, a random planar map which actually converges to the corresponding LQG, of course. So this is known. This is known that it is described in this way. And this can help us because somehow it can give us some intuition of how the behavior of the heat kernel should be in that case. So let's see one example. So if d gamma is the half dimension of gamma LQG, which by the way the explicit formula of this is not known, is one of the long-standing conjecture of the field of actually finding an explicit formula in terms of gamma, then the LQG distance, the metric distance, that the Brownian motion travels in t units of time behaves like t to the 1 over d gamma here, when t is very small. Now, why this is the case? The real reason for that is that the process is almost space-filling, in the same thing that I described earlier. For instance, in the context of gamma is equal to 0, when we do have the standard Brownian motion, then you do have the exact same behavior, but here gamma is equal to 0, therefore d0 is equal to 2. So here you have t to the 1 over 2, 1 over 2 is the exponent. Therefore, since this is just a time reparameterization of the standard Brownian motion, then here you have, instead of 2, you have the halves of dimension of the hull of the Brownian motion in the Liouville Brownian motion, which is d gamma. And also, coming back to the discrete picture, it is known that if you perform a random walk on a random planar map, and you run it for, let's say, 2 times n number of steps, then the probability that you get back to the starting point, it behaves like 1 over n, which is independent of gamma here. So this suggests that the heat kernel in the diagonal should behave like 1 over t. And here, that type of estimates here can give us some intuition of what the right answer should be in the case of the decay, or of the exact exponent, actually, exact behavior of the heat kernel, which again, it is expected to be sub-Gaussian, but the correct exponent, getting the correct exponent, however, is a different story. This can be challenging. Okay. And now that I have constructed, I have explained a bit the construction of the Liouville heat kernel, let me give you some background on some previous results towards that direction. There were already in the literature such results, in particular by Sebastian Andres, Naotaka Kahino, and also Meillard, Rode, Vargas, and Zeitouni, which actually proved bounds on the heat kernel with respect to the Euclidean distance and the time, but these bounds, they were far from sharp. But already from those bounds, someone would expect that you do have a sub-Gaussian behavior due to the fractal nature, of course, of the surface here. Another work of Ding, Zhang, and Zeitouni, actually, they proved some sharp bounds on the heat kernel, but only with respect to the time parameterization, not with respect to the metric. So see that this, as we shall see, this is indeed the correct exponent, but with respect to the time. But here the metric was missing in obtaining sharp estimates on the heat kernel. And here we do have the heat kernel conjecture, which was conjectured that the heat kernel behaves like this quantity here. So note here that this d gamma is larger than 2. So the exponent on t here comes from the work of Ding, Zhang, and Zeitouni, and here this parameter here, d gamma, comes from the fact that I described earlier that if you run your process for t units of time, then the expected metric distance that it covers should be t to 1 over d gamma, and that's where this d gamma comes from here. And we already see from the heat kernel, the conjecture here, that the heat kernel it was already expected that it presents some kind of sub-Gaussian behavior. This is not surprising because it's already known that if you perform diffusion processes on certain fractal sets, just like Sierpinski carpet on Sierpinski gasket, you do observe that type of behavior, sub-Gaussian behavior for small times. And in a recent research work of mine, together with Sebastian Adres, Naotaka Kahino, and Jason Miller, we actually verified the heat kernel conjecture when gamma is equal to square root of 8/3 for this special value. Now remember, this special value is a value of interest because it is the limit of uniform random planar maps. So this behavior was first conjectured for the scaling limits of uniform random planar maps, so that's why it was of interest in the literature. And moreover, we also give some sharp bounds up to a polylog factor of this little O1 term here in the exponent. So we give some sharp bounds which behave like a polylog. And the way we do it is that we introduce a new condition such that if you have a diffusion in a metric space where you also have a concept of an area measure, and if this diffusion satisfies this condition, then you observe that type of behavior. So you do have some sub-Gaussian behavior. So this condition can potentially, of course, be applied to various diffusions on fractals to actually deduce sharp bounds on the heat kernel. And similar techniques can also be used to solve the general conjecture for gamma between 0 and 2. Meaning that for general gamma, someone should be able to actually verify that this condition that this paper introduces actually is verified for the Liouville-Brownian motion for general values of gamma, and therefore resolving the heat kernel conjecture and actually obtaining potentially some precise estimates on the correction term here. And again, two motivations for someone who would care to actually study that type of estimates. In the first, because it sheds some light towards the spectral geometry of the surface by proving analogous results, just like Weil's law, and also some precise asymptotics on the eigenvalues of the Laplace Beltrami. Yes?
For this value of gamma, the square root of 8/3, is the dimension d gamma known, an explicit number?
Yes, that's a very nice question. Is equal to 4, because this corresponds to the so-called Brownian map. This is known. And the way that it is known in the case of the Brownian map is that the Brownian map has some kind of integrability, because the measures of the random planar maps is the uniform measure. So this is
So what is the dimension? Something easy, like 4?
It's like 4.
4. For the case when gamma is equal to square root of 8/3 is 4. For other values of gamma, an explicit form is not known as a function of gamma. Although we do have some precise, of course, estimates, but it's not known. We know the continuity in gamma. This is something that it is known. We have also some stronger continuity estimates, but it's not known the explicit function. And again, that's understanding better the spectral geometry of those surfaces was one of the main motivation of physicists to actually conjecture that type of sub-Gaussian behavior. And also again that it is known that if you have sharp heat kernel estimates for small time, then you can actually recover the metric, which was also another problem of interest in the case of geometry, of course. Okay. And now that I have described the first main result that I wanted to talk about today, let me describe the second main result, which is about properties of geodesics. So, yes?
I just had one final question about the heat kernel.
Yes, yes.
So, in general, the heat kernel can be written in terms of the sum of eigenvalues of Laplacian. Does that analog go over here? Is there such a thing as eigenvalues of Laplacian on these surfaces, and when you sum up, those eigenvalues, do you have a formula for the heat kernel in the Green's function, or does that break down?
Yes, it's an excellent, that's a very good question. Yes, you can make sense of eigenvalues, and yes, it has been recently shown, I think, that the heat kernel can also be expressed as a sum with respect to the eigenvalues, and also it has been recently shown that you can also prove an analog of the Weil's law that you have in Riemannian geometry. You do have it here in the context of LQG, yes.
So that would give you like some kind of like mixing time and long times of how quickly it approaches like a uniform distribution.
Exactly.
Okay, thank you. Sorry.
No, it's perfectly okay. It was a very good question, actually. I wanted to comment on that. So now in my second main result, I will describe about some properties of geodesics on this space. So here it's of course not obvious at all, but the metric that I described earlier, which is constructed by regularization procedure, actually is a geodesic metric. And that's something, of course, non-trivial. And here I will present some result towards understanding the geometry of how these geodesics behave. And we will see the behavior is very different than the Riemannian geometry. Okay, so let me start with the first main difference, which is in this type of geometry, we have the phenomenon of confluence, meaning coalescence. If you take, say, geodesics here in this context, and you target them at a fixed point, say 0, or even infinity, because we can also make sense of infinite geodesics, then the geodesics will merge before reaching their target points. Something that you don't see in the Riemannian geometry. This is due to the fractal nature. I will comment on that. And of course, the random environment. And you see here some very nice simulation where different colors indicate different metric distances by some fixed root somewhere here. And you see here these black paths, these are the geodesics, and as you can see, that already from the simulations, we can see that it has a tree-like structure. And the reason why it has a tree-like structure, the set of geodesics, is due to the phenomenon of confluence here. So this is already observed in simulations, and also in many other random environments, for instance, directed landscape. You do have that type of phenomenon here. So it is some kind of universal property in some sense in different random environments.
Well, the metric is kind of a random mountainscape or landscape.
Yes.
And so the geodesics prefer to go into the valleys and like a river
Exactly.
flow down to the center.
Exactly. That's a very good analogy. Exactly. And now why it is important? I mean, this, of course, it's interesting for its own sake, this question, but it also has some kind of consequences of understanding better the geometry of these objects. First of all, this shows that geodesics have some kind of stability. In the sense that if you fix a geodesic, say, between any two points, you pick an interior point of the geodesic, you change a bit your surface in a neighborhood around that point, then of course the geodesic will change, it's a global object. But the point is that as soon as the geodesic leaves that small neighborhood that you have changed your field, your surface, then it will tend to merge with the original geodesic, of the unperturbed surface. So this means, indeed, essentially the geodesic changes in the perturbed field only in a small neighborhood around the perturbation. So this means that the collection of geodesics, they have some kind of stability property. And also, it creates a link to other environments, because again, it's some kind of universal type property. So you see that this happens in other environments as well, and somehow the tools introduced here can also potentially be applied to other types of random geometries, and creating some kind of links with different types of fractal geometries. And now I want to talk about the specific property of these geodesics and how to strengthen it, which is, again, my main contribution towards that direction that I want to talk about today. So let's see one consequence of this phenomenon of confluence among the others. So here, suppose that we fix a geodesic. This is a geodesic, so this is the point 0. So this is deterministic, it is fixed. Then as a consequence of the confluence is that if you take any other geodesic, this is the geodesic P, if you take any other geodesic Q, such that it's sufficiently close to the original geodesic starting from 0, in let's say in the Hausdorff sense, either with respect to the Euclidean metric or the LQG metric, it doesn't matter because they use the same topology, although the geometry is very different, then geodesics will tend to form this chi shape here, locally, at least locally. And this is, of course, further justified by the tree-like structure that I described earlier. So locally, geodesics look indeed like trees here, as you can see. And one question, of course, that arises very naturally in this context is whether this is true for any geodesic starting from any point. This is not obvious because, of course, this the point is deterministically fixed. You can prove the same thing for a countable number of points due to the subadditivity of a probability measure. But in general, the accountable unions of sets of measure 0 do not necessarily are of sets of measure 0. Therefore, it's not obvious why this type of behavior happens everywhere. That with probability 1, at every point, if you start the geodesic and you approximate it sufficiently close by another geodesic, you have this type of behavior. A priori, it could be because we're in a fractal random geometry that you do have exceptional points. And the answer is that indeed we do have that type of property, and this is based on joint research work of mine together with a PhD student, Kavvadias, a recent work at MIT, that we actually show that this type of local behavior happens everywhere with probability 1. So at every single point simultaneously, if two geodesics are sufficiently close with each other, they form that type of structure. Now let's see a few applications of that. So why would someone actually care to actually prove that type of property? I forgot to mention that this property here the fact that this property happens everywhere, is the so-called strong conference property. That's how it is called. Okay. Now let's see certain applications of strong conference. One application is that if you consider the collection of the interiors of all geodesics, then this collection forms a tree, which again is not obvious a priori that is true from confluence, because it might be the case that if you fix 2 points on the interior of geodesics, there are multiple points connecting them. In that case, the tree structure breaks down. But it turns out, as an application of the strong confluence of this property, there's a unique geodesic connected to interior points of a geodesic. While at the end points, a priori, actually there are points where you have multiple geodesics connecting them, but not interior points. And that's what makes here to have a tree-like structure. And this, of course, is confirmed by the simulations that I showed you earlier. Another property is that if you take this set here, the union of the interiors of all geodesics, which is a tree, someone might ask how large this tree is. So this was, again, has been conjectured that this tree has the same size in terms of Hausdorff dimension with a single geodesic. This has been studied extensively in the Brownian geometry, meaning that when gamma is equal to square root of 3/3, and also in other types of environments, just like the rectal landscape. It was a conjecture whether the same is true for all values of gamma. And it turns out that as an application of this strong confluence, it is indeed this set is as large as a single geodesic. Therefore, verifying this conjecture. And finally, we can potentially use that type of behavior to compute Hausdorff dimensions of exceptional points. In LQG, there are points where the so-called K-star points, where they can connected by K number of different geodesics. Something, of course, that doesn't happen in Riemannian geometry. And usually, it's very challenging to compute Hausdorff dimensions in that setup. But this gives a variety of tools, this property, to actually understand better the geometry of these exceptional points and how large this set is and how they actually behave. So these are a few applications of that type of property, which are, of course, based on ongoing research work. And this is the second main result about shedding some light into the geometry of those spaces. And let me now move on to the third main result of my talk, which is continuity in gamma. So let me motivate you a bit why this problem is interesting. The motivation comes from physics, because remember, as I described earlier, these surfaces, they arise as scaling limits of random lattice models or random discrete models coming from physics. These models have some parameters, they depend on certain parameters, and the very natural question that physicists ask is how these models change in the large scale if we perturb the parameters in a continuous way. So in our world, this is translated in how gamma LQG behaves if gamma changes in a continuous way. And another conjecture was that if gamma tends to 0, we actually get the smooth Euclidean surface. And now let me talk a bit of why this problem is non-trivial. The main reason for which that makes this problem being non-trivial is that there's no direct way to construct the metric, the volume form, the boundary length measure, the curvature, etc., without using regularization procedures, but just directly from the field. And this makes it hard actually to deduce some kind of continuity in the parameters of this surface. And you see here some very nice simulations made by Jason Miller that this represents here discretizations of these LQG surfaces, where here for different values of gamma, as you can see here, where different colors indicate different metric distances. And you see here that this can behave quite differently for different values of gamma, so it's not obvious even at looking at simulations why there is some kind of continuity in gamma of those spaces, due to, of course, to the fractal nature of those spaces.
Could you explain a little more what the picture is showing? I didn't quite understand what the colors are. You said metric distances, but between 2 points, or between a fixed point and other points, what?
Yes. So here there is some kind of fixed point here. There's a fixed point, and these colors indicate different distances in some kind of approximation scheme of LQG.
So you're saying it's the distance to a fixed point somewhere in the plane?
Yes, exactly. We live on the plane now. We have a certain bending, a discretized version of the LQG, and we're looking at distances here from some fixed point, let's say 0. We are in a large box, and we fix the center of the box, and we see how the different distances.
Light blue is close, and darker blue is further away.
Exactly.
Mountain tops, which are, even though they're sort of closer in the Euclidean sense, they're harder to get to.
Exactly.
Mountains.
Exactly. That's the point. And you see here the behavior is very different. So this means that even looking at simulations, it's not clear whether you have some kind of continuity here. Now, as for the area measure, it's not that hard to actually show continuity, because that follows by standard theory. For instance, someone can use Kolmogorov criterion, because there are some explicit formulas there, and it's not that hard to see that the corresponding area measure behaves continuously in gamma. But unfortunately, this is not the same for the metric. You cannot use some soft arguments to actually deduce continuity of the corresponding distance function. And in a recent work of mine, I actually proved that the corresponding distance function is continuous in gamma with respect to the local uniform topology on the product of the complex plane with itself. And I also proved that as gamma tends to 0, then the LQG metric converges to the Euclidean metric, actually.
In what sense?
With the local uniform topology on this space here.
Oh, so if I take a patch, it has some area in the sphere, although it depends on which random sphere I take, so I have to get a distribution of areas for that patch. And you're saying that distribution is a continuous function of gamma.
Yes.
The area of the patch itself doesn't really make sense, because it's the distribution of areas.
Exactly. So I do prove that type of result, therefore verifying conjectures coming from physics. So there is some kind of stability, in other words, of this LQG, of this object with respect to the parameters. And now that I have presented three main results, contributions of mine towards understanding better LQG theory, let me proceed with a question which is extremely interesting to me, which I really like. And that's an analysis question. Essentially, I will talk about conformal welding, conformal removability, and how these things appear in a natural way in the context of LQG theory, and of course SLE theory. As we will see later, there is a way somehow to glue these surfaces together along their boundaries, to weld them, to produce interfaces which are SLE curves. And I will also motivate you of where this essentially comes from. Okay. Now let me start defining the main questions. So let me start by conformal removability. So here remember, we learn in a standard course in complex analysis that a subset of the complex plane is conformally removable if every homeomorphism to the complex plane, which is conformal on the complement of the set, is conformal everywhere. Now, conformally removable sets exist. I mean, the most simple example are singletons. Singletons are conformally removable sets, but also there are sets which are non-conformally removable. For instance, sets with positive area, with positive Lebesgue measure. These sets are non-conformally removable. And also there are sets with zero Lebesgue area, with zero Lebesgue measure, which are non-conformally removable. And I'm going to mention some of those sets, just like Serpisi carpets, Serpisi gas, Cantor type sets, and etc. There's an entire theory, very rich literature towards that type of questions. Now, how someone can prove conformal removability? So one of the famous conditions, geometric condition to prove conformal removability, is due to Jones-Smirnov, which actually proved around 25 years ago that if you have a set whose boundary, which is the boundary of a Holder domain, by Holder domain I mean a simply connected domain, such that if I take a Riemann mapping from the conformal transformation from the unit disk onto that domain, then this is Holder continuous. Such a mapping exists by the Riemann mapping theorem. Then the boundary of such domain is conformally removable. So there are geometric conditions which actually guarantee, which are sufficient for conformal removability. More generally, they showed that the Riemann map doesn't have to decay, the modulus continuity doesn't have to decay to 0 as strong as that of a Holder domain. It can be relaxed a bit, so it can decay a bit more slowly to 0. It can decay like this exponential of the square root of the logarithm, essentially here. So if the modulus continuity is of this form, then we have conformal removability of the boundary of the domain. However, someone might wonder whether there is some kind of unified geometric condition or unified measurable way somehow to recover, which is necessarily sufficient for a set to be conformally removable. But the answer is no, because due to a very nice paper by Chris Bishop called Conformal Removability is Hard, it is shown in this paper that if you take the collection of all conformally removable subsets, say of the unit square, then this collection is not the Borel set with respect to the Hausdorff distance. So meaning it is not possible to come up with a measurable way which can actually characterize all of the conformally removable sets. So in other words, these conditions here, geometric conditions introduced by Jones and Smirnov, they actually miss a lot of conformally removable sets which do not satisfy these conditions. As we will see, of course, later. SLE4 is one such example. Okay. Now let me discuss a bit about another favorite question of mine, and that is the problem of conformal welding. So here for that, we start with a homeomorphism defined on the unit circle, from onto the unit circle. Then a conformal welding is essentially a Jordan closed curve on the Riemann sphere, such that the following is true. Remember the Jordan curve theorem says that this curve divides the sphere into two simply connected components. Then if we take conformal transformations from the unit disk onto each complementary connected component, and we restrict them on the boundaries of their domains, then we get phi and we compose them. Of course, there might be several such maps. If we find two maps satisfying this property, then we say that eta is the welding interface corresponding to the homomorphism phi. Existence is not obvious at all. And in fact, there are exceptional homeomorphisms for which you cannot find a welding interface. Then what's the link with conformal removability? If you know that the welding interface is conformally removable, then it is the only curve that can arise from the welding homomorphism phi modulo Möbius transformation, meaning that any other welding interface which solves the welding problem corresponding to phi is the image of the original welding under a Möbius transformation. So it is unique modulo Möbius transformation. Okay. So these were two analysis questions which are again, as we shall see, arise very naturally in the context of LQG theory. Now the next thing, of course, to introduce is somehow to explain how the welding, the gluing of LQG surfaces takes place, and where the motivation comes from for that. And also explain what the right interface should be, why SLE is the right interface when you actually glue these fractal surfaces. And the motivation of this somehow conformal mating of surfaces comes from conformal matings in complex dynamics. Let me explain very briefly the related theory. So here, suppose that we start with a monic polynomial, complex polynomial of degree at least 2. Then for such a polynomial, we can define the corresponding Fatou set, meaning that it is the set of all points in the complex plane, such that if we compose the monic polynomial n times with itself and evaluate it at the point z, then in the limit as the number of times that it is composed to itself, as the limit as the number of times tends to infinity, then you get infinity. So this is the so-called Fatou set. And then we can define the so-called Julia set, which is the boundary of the Fatou set. And then it is known that if you start with two monic complex polynomials of degree at least 2, such that the corresponding Julia sets are connected, then there's a way to glue them together to produce a topological sphere. And the gluing, of course, comes, the point is that these Julia sets, they have a natural parameterization, and then gluing them according to this natural parameterization, you can actually produce a topological sphere, and also this defines a conformal structure as well, meaning a way to embed the resulting object into the Riemann sphere. And here there are some very nice simulations of how these sets can look like. These Julia sets can vary, can be very different in the shape. They can look like, they can have this dendritic-like shape, but they can also look like trees of disks, as you can see here. And now there's a very natural question arising here. What happens if instead of deterministic objects here, just like the Julia sets, I have random objects? For instance, what happens if I take two random trees and glue them together in some way? What happens in that case? Or what happens if you have two random trees of disks and glue them together? What happens? What do I get? So this should be the random analog of this procedure in some sense, of course. But before we construct some kind of random analog theory of some kind of conformal mating of either trees or trees of disks, we need to understand what the welding interface should be. What's the main candidate? And the main candidate is the so-called Schramm-Loewner evolution, or just SLE with parameter kappa. So this, you can imagine it to be a one-parameter family of probability measures on the sets of planar fractal curves. So as you can imagine that these curves live, say, in the upper half plane, starting from 0 and terminating at infinity. And this space can be endowed with a Hausdorff distance. Therefore, it is a Borel metric space. And on that space, you can define probability measures. The case when kappa is equal to 0, just like remember the analogy with LQG, the case kappa is equal to 0 corresponds to a straight line, in the same sense that 0 LQG corresponds to the Euclidean space. But however, if I take kappa positive, and as kappa increases, then the curve becomes more and more rough. It has a very deeply fractal nature, as you also see here by the simulations. This is simulation of an SLE2, SLE3, and here we do have an SLE6. I will comment on the behavior of the curve depending on the value of gamma. These objects are very natural, in the sense that they arise as scaling limits in certain two-dimensional statistical mechanics models of criticality. For instance, SLE2 describes the scaling limit of the loop-erased random walk. SLE8 describes the scaling limit of the self-avoiding random walk. And SLE6, for instance, it describes the scaling limit of the interfaces in percolation clusters. So they this family is a very natural family in the context of statistical mechanics as well. A very fundamental property of that is that they're conformally invariant, meaning that if you take an image of such a curve, let's say the image is in the upper half plane, you take a conformal map from the upper half plane onto the upper half plane, then the image of an SLE kappa in the upper half plane under that map is an SLE kappa curve in the upper half plane. So in that sense, the curves are conformally invariant. And of course, the behavior is very much different. For instance, if kappa is between 0 and 4, including 4, then these curves are simple almost surely, in the sense that they do not intersect themselves a second time, as you can see here by these simulations, this fractal nature. When kappa is between 4 and 8, the curve intersects itself. It can also intersect the domain boundary in multiple points, therefore creating halves, meaning regions which are disconnected by the curve from infinity. As you can see, this one region, this second region, and there are other regions here, very small ones, which are disconnected from infinity. When kappa is between 4 and 8, but without the curve being space filling. And when kappa is at least 8, the curve is space filling. It hits every single point in the complex plane with probability 1. So the behavior can really vary. Okay. And now that I have motivated you about how the question of where the question of conformal welding comes from, let me now explain the first main result. So Sheffield proved that if you take two LQG surfaces, say parameterized by the upper half plane in this case, you glue them along their boundaries. There's a constant of boundary length as well. Again, using regularization procedures, you can construct in a similar way. You can construct the boundary length. You glue them together according to boundary length. Then here on the bottom, you get another LQG surface together with an interface, which comes from this welding procedure. And the point is that this welding here, this welding interface, is an SLE kappa curve when kappa is less or equal to 4. At least when our surfaces, they have this, the topology of the upper half plane. So here, of course, the case when kappa is equal to 4 corresponds to the critical case. And this is the 2 LQG. LQG with parameter 2 is the so-called critical LQG. Now what happens in a non-simple case? In that case, the picture can be slightly more complicated because SLE kappa curves in that regime, they're non-simple, they intersect themselves as we saw, they disconnect regions from infinity. Surfaces which are parameterized by the upper half plane is not the right object to glue. So here, in analogy to the theory of the Julia sets, we need to glue trees of disks. Random trees of disks, of course, which is the so-called stable loop trees. This is an object arising very naturally in the theory of Liouville processes. And here you have a trees of disks. They do not intersect each other, by the way, but you can imagine here there are accumulation points of disks. And there's a concept of natural parameterization on the boundary of such an object. Therefore, in an analogy, in a similar spirit, just like it happens with the Julia sets, you can actually glue such objects, independent objects along their boundaries based on that natural parameterization to produce a new surface, and the welding interface is an SLE kappa curve, in the non-super regime. In other words, SLE kappa curves for every value of kappa between 0 and 8, they arise naturally, as you can see, as welding interfaces when you glue these random fractal objects. Therefore, the problem of conformal immovability of SLE kappa when kappa between 0 and 8 arises very naturally, as we explained earlier, because essentially gives that this procedure has a unique solution, and the solution is the SLE kappa curve. Okay. And now let me briefly mention the result, which actually has initiated a lot of literature. It's a very active research area right now in probability. That the pioneer work of Duplantier, Miller, Sheffield proved that we can have the analogous procedure that I described earlier in conformal matings in complex dynamics, meaning that you can take two random trees here, you glue them together in some way, and then you get a new LQG surface, which is parameterized by the Riemann sphere. And you can do the same, but instead of these trees, you have trees of disks. That's the analogous construction. And they actually proved that this has an analogous, this is the random analog. And the point is the third construction of LQG. So meaning so far we have described two ways to do it. A third way is by gluing random trees or random trees of disks. And now let me focus on the problem of conformal immovability of SLE kappa, which is the last main result that I wanted to talk about today. So when kappa is less than 4, it has been shown, it was shown by Rode and Schramm, that SLE kappa is the boundary of a Holder domain. Therefore, by the Jones-Smirnov condition, it will be conformally removable. But this doesn't happen at kappa is equal to 4. So this breaks down. If you consider the corresponding Riemann map, the modulus of continuity decays to 0 much more slowly than the one coming from the Jones-Smirnov condition. So you have this logarithm here. And this was another conjecture on the field. And we actually resolved this conjecture in a recent joint work with Jason Miller and Lucas Sub. So meaning that all, at least the conditions coming from the Jones-Smirnov paper do not apply in the case of SLE4. So this made the problem, this was essentially the main difficulty in actually proving conformal immovability of SLE4. Now in the non-simple regime, the flavor of difficulties is different. And the difficulty here is, again, the complement of SLE, you have countable collection of simply connected domains. So it's not the boundary of a simply connected domain anymore. And then Jones-Smirnov condition only concerned boundaries of simply connected domain. So there was no known condition that actually could potentially be applied in the case of SLE kappa to deduce conformal immovability here. In general, it can be very subtle, actually, conformal immovability of boundaries of non-simply connected domains. And let me give you two examples of such sets, which actually motivate a bit the solution of this problem. So here first we have the Sierpinski carpet. So how to construct the Sierpinski carpet? You start with a unit square, and you just, at every step, you remove the middle square. And you just iterate this procedure again and again, and at the end you get a fractal set. You get a fractal set. And it's not that hard to show that this fractal set is not conformally removable. There's a soft argument to actually show that this set is not conformally removable. However, if you do the same, but you replace square with triangles now, and you remove the middle triangle, and you iterate, then you get another fractal set, which is the so-called Sierpinski gasket. And it was shown in a very nice paper by Dalambekos, who was here at Stony Brook, that the Sierpinski gasket is not conformally removable. So he actually proved that in a very nice paper. It was a difficult paper. Now, what is the main difference? Why the problem of non-conformal removability of the Sierpinski carpet is much easier than that of the non-conformal removability of the Sierpinski gasket? Now, the main difference lies on the boundaries of complementary components. Remember, every time that I remove a square, the squares do not intersect on their boundaries. So meaning that the complementary connected components of the Sierpinski carpet do not intersect. While and somehow this makes it easier to construct exceptional homeomorphisms, which are conformal in the complement but non-conformal everywhere. However, in the case of the Sierpinski gasket, the boundaries of two complementary components may intersect. as you can see in this picture here, you see, for instance, this point here is a boundary, this is intersection point of the boundaries of these two squares, two triangles, and you can have it, I mean, everywhere, that type of intersection points. And this somehow it proves, it makes the problem of constructing an exceptional homeomorphism, which is conformal on the coupler but not conformal everywhere, very hard. Because what you have to do essentially, the problem reduces to controlling the variation of the homeomorphism around points of intersection. Because essentially in 2 dimensions conformal mobility is essentially equivalent to proving the ACL property, that any such homeomorphism is absolutely continuous on lines. And to do that, you need to control the variation of the homeomorphism near the points, on the points of the fractal set. And these intersection points here actually makes it hard to do that. So it's not easy to actually construct an exceptional homeomorphism. But it can be done in the case of the Sierpinski gasket. So SLE kappa, at a very high level, of course, should be considered as the analog of the Sierpinski gasket, in the sense that, again, here in the non-simple regime, the boundaries of 2 complementary connected components can intersect each other. So you actually have the same difficulty there. If, in order to construct an exceptional homeomorphism, or in actually to prove conformal mobility, you need to control the variation of such a homeomorphism near the points of intersection of the boundaries of 2 complementary connected components, and that can be cause several difficulties. But here, luckily, there is one fundamental difference. And the fundamental difference is here you have a single point of, you have finitely many points of intersections, while in the case of SLE, if 2 complementary connected components intersect, they will intersect at many, many points. In fact, the half dimension of that set is 3 minus 3 times kappa over 8. So somehow this is a large set. Meaning that if you have a point here which is not that regular, which is a bad point, where the variation is not under control of such a homeomorphism, you can always find very close to it other points which are regular enough. So you do have a variety of points. And this is what makes it possible to actually control the variation and essentially prove the ACL property, and therefore prove conformal mobility for a certain range of kappa that I'm going to specify. Okay. And now let me describe my main results towards that direction. So in a joint research work with Jason Miller and Lucas Sug, we actually proved that if you have an SLE4 in the upper half plane from 0 to infinity, then the range is conformally removable with probability 1. Meaning that any homeomorphism mapping the upper half plane onto the upper half plane, which is conformal on the complement of the curve, has to be conformal everywhere. That's what conformal mobility, that's what it means in this context. Now, for general values, answering, of course, here a question posed by Sheffield. Now, what happens in the non-simple regime? In the non-simple regime, we focus on specific values of kappa. We focus on the values of kappa for which the graph of complementary connected components of SLE is connected. Meaning that if you take, with probability 1, meaning that if you take an SLE kappa in the upper half plane, a curve growing from 0 to infinity, so here we consider the values of kappa such that the following property holds. If you take, let's say, one connected component here, this one, and this one here, there is a chain here inside this set which actually connects via finitely many connected components, this component, say, with this component, such that if you take 2 consecutive components on the chain, their boundaries intersect. And we want this to happen for every single component with probability 1. So we look at a very special, this is calligraphic kappa, which is the set of these special values of kappa for which you do have this connectivity property. And we prove again with Jason Miller and Lucas Sug that for these values of kappa, the range of an SLE kappa in the upper half plane from 0 to infinity is conformally removable. When kappa lies in this connectivity regime, therefore answering another question towards conformal removability of SLE kappa in the non-simple regime now. Of course, if this set here were an empty set, this result wouldn't make sense at all. But luckily, Gwynne Pfeffer proved that this set is a non-empty set. And someone might wonder whether this set is the entire interval with endpoints between 4 and 8, but it turns out it has been shown in a recent work by Liu and Zhuang that this set here is not this interval, and in fact they prove that if kappa is very close to 8, then the range of SLE contains a topological Sierpinski carpet, and therefore it's not conformally removable. So when kappa is close to 8, we don't have conformal removability, and as a result, this connectivity property breaks down, of course. And here we have a conjecture about what would be the right values of kappa for which you do have connectivity. And there's a conjecture that this should be the interval between 4 and 6. And the reason for that is that the value 6 is very special because somehow SLE6 arises as the scaling limit of interfaces between clusters in percolation, and the symmetries happen in percolation. Somehow in the percolation model we have more tools to actually study several problems, and somehow the value 6 appears as a critical value on many different questions. Also remember, SLE6 corresponds to the limit of uniform planar maps, random planar maps. So somehow it is some kind of critical value that appears quite often. And now how we prove this? Let me say briefly a few words and then conclude my talk. In order to prove that type of question, motivated of course partially by Dalambekos paper on the Sierpinski gasket, we introduce a new geometric condition for a set to be conformally removable. So, for sufficient, of course. It cannot be necessary due to the result of Chris Bishop that there's no possible way to actually characterize the conformally removable sets in a measurable way. So we introduce a new geometric condition which is sufficient for a set to be conformally removable, and this condition here applies to boundaries of sets which are not boundaries of simply connected domains. Which it was something again was quite subtle as we saw earlier, therefore making progress towards that direction as well. And we prove that SLE kappa here, for those values of kappa here for which you have this connectivity property, satisfies this new condition with probability 1. And the same of course for SLE4. And this condition can be actually applied to prove conformal removability for a variety collection, potentially for a variety collection of fractal sets which are not boundaries of simply connected domains. And also, this also has another application in the context of LQG theory, that if you take any fractal set which arises in a natural way in the context of LQG and SLE, not necessarily SLE, whose graph of components is connected, then it's very likely that this will actually satisfy this geometric condition. This also ongoing research towards that direction. Therefore, proving uniqueness of versions of the conformal welding problem where the welding interface is not necessarily an SLE kappa curve. And with that, I would like to conclude my talk and thank everyone again for giving me the opportunity to give the talk and meet so many nice people here.
Questions?
Well, I have a few, but maybe I should leave them for later.
I have a question.
Yes.
So I think maybe some time around like slide 25, there was this question that Chris asked about this interface between like this dark blue and light blue. And it seems that there are some regions in which the metric kind of like becomes worse. And so
That much further.
Yes, yeah, I think I understand the slide. Yeah, you mean here. Yes, exactly, yeah.
Could this be understood in some way in which areas this happens? That it's like some sort of like doubling of the metric?
Yes, I mean, this is a very good question. This is related to the thick points of the Gaussian free field. So there are special points where if you take the circle average of the Gaussian field in small circles, then this has very different behavior. There are points where this behaves, grows very fast or very slow, and this is reflected. That's why you do have that type of behavior here. Essentially, you can, if you want to think about in terms of the Gaussian free field, then these regions indicate different types of thickness points of the Gaussian free field.
Is there some result of the type, like if gamma, the LQG variable like is small enough, then the area of that region is like also small?
Yeah, I mean, this should be translated into results in the, probably you mean volume estimates of the LQG area measure. Yes, there are estimates, yes. There are estimates in terms of gamma. That's true.
I have another question.
Yes.
That's related with the thing at the very end. You mentioned that the conjecture for these
You mean probably the last slide?
mathematical K is that it's the interval 4 to 6.
Yes.
But 6 is an explicit value. Like, I mean, you know that that this conformal over some, well, it comes from like as a limit of percolation, right? That by Smirnov's result.
Yes.
Like that seems like, well, it's like a very explicit.
Yes, it appears somehow it is some kind of critical value. It's so if you take kappa when it's not equal to 6, then you don't get uniform monoplanar maps anymore. So somehow there is some kind of symmetry there, value, some kind of explicit integrability as well. This is related to the Brownian map, square root of a third LQG, where the Brownian map can also be constructed in terms of diffusion theory. There is a way to access. There's an alternative approach due to Legal and many other people in the area, and then Miller and Sheffield show that the object that you get, if you do this exponentiation that we described at the beginning of the slide, then the object is the same with the Brownian map constructed from that type of perspective. So you do have some kind of integrability. So that's essentially the reason why SLE6 is very special.
No other questions? Then let's thank Kostas again.